section 2.3, we return to trees and try to prove some results about trees based on some of what we learned about cut vertices and cut edges. So remember, a tree is just a connected graph that has no cycles. And we can extend that idea to a forest, which is just any graph that contains no cycles. So it doesn't have to be connected anymore. Although technically, you could have a tree be an example of a forest, right? So another way of saying this is to say that a forest is just any graph that has no cycles, and a tree is a connected forest, right? So for example, right, this would be an example of a forest because there's no cycles, but it's not a tree because it's not connected. This is also an example of a forest because it has no cycles, and since it's also connected, we call it specifically a tree. And by looking at all those examples that we did in the warm-up, it seems that any tree of order n is going to have size n minus 1. So if we want to prove this, we need to use something called strong induction. So probably you've seen proof by induction before, where you start off by proving that the base case of a particular statement is true. And then to prove that the statement is true for all n, you assume that it's true for some k, where k is greater than or equal to the base case, and then prove that it's true for every k plus 1. Right? Assume it's true for k, prove that it's true for k plus 1. So strong induction is similar, but it's a little bit stronger in a sense. Your induction hypothesis is a little bit stronger. So just as a review, or if you've never seen this before, in a strong induction proof, you want to prove a statement P of n is true for every natural number n. And you do so by first showing that P of 1 is true. That's the base case, or sometimes your base case will start at 2 or 3 or something. But depending on what you're trying to prove, if you're trying to prove it's true for all natural numbers n, then you have to start off by proving that P of 1 is true. Then what you're going to do is assume that P of k is true for every k less than or equal to n. And we should say for every k between 1 and n for some natural number n. And if you assume that, you then have to prove that P of n plus 1 is true. So this is slightly different from a regular induction proof because we're assuming it's true for every possible k between 1 and n, and using that assumption to prove that it must also be true for P of n plus 1. Right? We call that the strong induction step. Right, so we're going to prove that a tree of order n has size n minus 1 by strong induction on n. So the first thing we need to do is prove that it's true for the base case. In other words, we need to show that a tree of order 1 has size 0. Okay, so let's let T be a tree of order 1. That means it has one vertex, and to be a tree means it's connected and it has no cycles. So you couldn't have any loops or anything, there's no cycles here, and so it can't possibly have any edges. It has size 1 minus 1, which is 0. So we've proven that the statement is true when n is equal to 1. So we've proven the base case. Okay, the base case is usually the easy step. The harder step is the strong induction step. So what we're going to do for the strong induction step is let n be greater than 0 be some integer, and suppose that any tree of order k has size k minus 1 for any k value between 1 and n. Right? So we're assuming it's for every possible k between 1 and n. We then need to show that any tree, we must show that any tree of order greater than n, let's say order n plus 1, has size 1 less than the order. So n plus 1 minus 1 has size n. Right, so assume that the statement is true for any tree of order n, and prove that it's true for a tree of order n plus 1. Okay, so let's let T be a tree of order n plus 1. We need to show that it only has n edges. Okay, so remember what we know about trees. We learned we learned 2 sections ago that in a tree, every single edge is a bridge, right? It's a cut edge. If you deleted any single edge in a tree, you're going to disconnect the graph. So every edge of T is a bridge. So let's let UV be an edge of the graph, an edge of T, and consider the graph T minus that edge. So if you took your tree, whatever it looks like, I don't know, right, some branch off, and you delete one single edge, UV, right? Well, because that edge is a bridge, we know that the resulting graph is disconnected. And so how does that help us? Well, it's going to leave us with two sort of subtrees here, right? It's going to leave us with two components. The resulting graph has two components, which we'll call T1 and T2. And those resulting components have to be trees as well, right? Because you're not going to introduce any new cycles by deleting an edge, right? So these T1 and T2 are also trees, and let's just say that they have order, let's call them K1 and K2 respectively. Okay, so you deleted this one edge, you're left with these two components that has, let's say, K1 vertices over here and K2 vertices over here. You haven't deleted any vertices of your graph, which means that K1 plus K2 altogether has to be equal to the size, or the order, sorry, of the original tree. So note that K1 plus K2 must be equal to the order of the original tree T, which is n plus 1, because we didn't delete any vertices, we only deleted a single edge. Okay, now what we can do is we can apply the strong induction hypothesis. We can apply this hypothesis here. This is why we need it to be strong induction, because I don't know necessarily that this has exactly n vertices. I just know that it has some number of vertices that's less than n plus 1. All right, so since K1 and K2 are each less than n plus 1, in particular, that means they're less than or equal to n, which means the strong induction hypothesis applies. Right. The hypothesis holds here, and so we can conclude that the size, right, the number of edges in these two components are going to be K1 minus 1 and K2 minus 1. So there are K1 minus 1 edges in the first component and K2 minus 1 edges in the second component. Now remember, we're trying to prove that our original graph T has order n, right? We need to show that a tree of order n plus 1 has size n. Right? We're trying to show that the original graph has a total of n edges. Okay. Well, the size of T is just going to be the size of T1 plus the size of T2 plus that one single edge that we had deleted. Right? So it's going to be K1 minus 1, that's the size of T1, plus the size of T2, which is K2 minus 1, and then plus 1 for that one single edge UV that we had deleted, right? This is part of the original graph T, so we need to include that in the size of T. All right, so we can rewrite this then as K1 plus K2 minus 2 and then plus 1. Or we can just cancel out one of these, and we're left with K1 plus K2 minus 1. But remember, we had also said that K1 and K2 added together gives you n plus 1. Right, because the vertices of this component plus the vertices of this component account for all the vertices in the entire original tree. So this is really equal to n plus 1 minus 1, right, because K1 plus K2 is equal to n plus 1, which finally, that's going to simplify to n. So we've proven that in a tree of order n plus 1, the size of that tree would be n, which is what we were trying to prove. So this completes the induction step. And so now, by the principle of strong induction, we can conclude that for any tree of order n, the size is n minus 1. Now we can extend that to the broader class of forests, right? A forest is sort of like a tree in that it has no cycle, but it doesn't have to be connected, and get corollary 2.3.2, which says that a forest of order n with k components has size, well, what would that be? So one way to think about it would be, let's maybe just draw a picture. Okay, so here's my example. I have 1, 2, 3, 4, 5, 6, 7 vertices. I have 3 components, right? This sort of T-shaped thing, this one and this one. And the number of edges also happens to be 4. So it would seem maybe 7 minus 3 is the number of edges. In fact, this is correct. A forest of order n with k components is going to have size n minus k. Okay, so how do we prove that? Well, this follows from the fact that, I'll get this covered up for the next video. If we want to prove this, note that if a graph G is a forest with n vertices and k components, each component, each of those k components is a tree. Let's say each of those trees has order, I'll call it n sub I. Okay, and so we would have to have that when you add up the order of those individual components. So if there's k components and we add up the order of the original components, it has to add up to n. And so the size of the forest, right, the number of edges of the forest, must be, well, remember each one of these trees, each one of these components is a tree of order ni, and we proved in the last theorem that the size of that individual component would be ni minus 1. So I goes from 1 to k. If we sum up the size of each of the individual components, well, the sum of the ni's is going to give you n, and then we have a -1 k different times, right? -1 in the first case, in the second case, all the way up to the kth case. So that means the size would be n minus k, which is what we thought. So in the next video, we'll talk a little bit more about trees and forests and what we can say about the number of edges in a connected graph.